All right, are there any, hopefully you all got the email about the mistake I made at the end of the last lecture. That'll happen from time to time. Feel free to point out what I'm doing wrong. That is fine with me. Are there any questions before we get rolling? Yes?
Of course I have a question.
Yeah.
Not like there's no other serious questions, but, okay. Who would win in a fight, 40 comp sci or all of administration?
40 comp sci.
Like 40 comp sci majors.
Oh, 40 comp sci majors and all the administration?
All writing years. It's not all seniors, it's not all freshmen, but 40 comp sci majors.
Well, this depends. Are we including the athletics department? Yeah. Yeah, I mean, you know, if you put the athletics department with the librarians, whoo, they can kick ass. I don't.
None of us can hear you.
None of you? Oh yeah, I gotta turn this on. Yeah, thank you for reminding me. Okay, now you should be able to hear me. We just told a couple of jokes. Don't worry about it. But thanks for reminding me, Ross. I had to turn it off because I was apparently interfering with the colloquium. Okay, so today is going to be a little bit painful. Hopefully, though, it will clarify something for many of you. But our goal today is to get through the topic of vectors. Vectors are something you've seen a million times before, but we are going to give them a very, very formal treatment. And then on Thursday, after you take your homework quiz, which will be the beginning of class on Thursday, we are going to finally transition to something very different, okay? We're going to talk about dual vectors, which is going to be our segue into tensors. Tensors we might not get to until next Tuesday, but that's fine, okay? So this is where things are hopefully going to make sense. And also, I would say I've done scattered things in my treatment of special relativity, but what I'm doing today and what I'm doing over the next couple of days is a story which we will repeat almost in detail for the case of curved space, because these are the very important tools that underlie general relativity. So this is where you really want to pay attention. This isn't a passive topic. Okay, so we're going to start with a brief review of what we call index notation. This is a tool we're going to use throughout this course. Many of you have used it in some context or another. We have a very precise way of using it, so I want to illustrate this. So first of all, so far we have illustrated all of the quantities that we work with in terms of matrices. So we have, vectors, we have the transformations that we do on those vectors, be they boosts or rotations. We have the metric, which defines the space, and the transformations thereupon. All of those could be represented by vectors. There are three reasons why matrices suck. Okay? And these are three really important reasons. Number one, they can be big. Okay, hopefully you realize this from quantum mechanics, where you're secretly working with an operator that can be represented by an infinite dimensional matrix. How many of you actually write down those matrices? Right, okay. Saw you raise your hand in the back. Okay, so matrices can be really big, and writing them out explicitly can make you really tired. We're never going to have to deal with anything larger than 4x4 in this class, but nonetheless, if you had to write down 4x4 matrices time and time again, you'd probably get tired and would want to do it. 2, matrices do not commute. Okay, one of the important properties of matrix algebra is that you have to be very careful about the ordering of terms, because you can't just take two matrices and swap their places and then do the multiplication, because you'll end up with a different answer in most cases. Not in every single case, but in most cases. And perhaps most importantly, we will encounter objects that can't be represented by matrices. Okay, so far, everything that we've encountered, the metric, the transformations, the vectors that the transformations are acting on, those could all be represented by matrices, but we're very quickly going to stumble upon objects that we are required to use in this course that cannot be represented by matrices, okay? Now there is this idea that you can represent them by cubic or hypercubic matrices, but you know, how many of you want to try and write down a hypercubic matrix? Yeah, that's what I thought. Many people are like, I could write down a cubic matrix. You can, but a hypercubic matrix, I don't think you want to try and do it. At any rate, so we're going to find things that can't be represented by matrices. Fortunately, everything that we encounter can be handled with index notation. So we're basically abandoning the matrix representation, okay? And what we're going to find is that with index notation, the expressions become really, really small, okay? Better still, with index notation, the things commute. You don't have to worry about the order of things. Woo! That's pretty sweet. And third, and most importantly, with index notation, you can describe any object, okay? So the lesson I'm about to give you is going to be very, very critical for everything that we're going to do. So here we go. So I'm going to illustrate the basics of index notation with a familiar example. So we're going to take the point x1, x2, sorry, x1, x upper 1, x upper 2, if I'm going to use upper labels. So I've got a coordinate system x1, x2, and I've got the point labeled by its coordinates x1, r2. This is on r2, so that's just flat real space of 2 dimensions, nothing weird. And then what we want to do is we want to rotate the coordinate system. Okay, so I'm going to draw the pre-rotated coordinate system and then the post-rotated coordinate system. And we're going to rotate it by an angle theta. Okay, and what we're interested in doing is using index notation to find that the components of the same point, this is the same point in space, okay? But we want to find the new components of that point in this new rotated coordinate system. Now this is something which we've covered before, obviously. We just take a vector and we rotate it with a rotation matrix, okay? So this is something we've covered before, but now, instead of using the matrix language, we want to translate this to the index notation language, okay? Now I will write down the matrix just so that you can remember what to expect, but I certainly want to transcribe it into matrix language. So in matrix language, what we have is that x1, x2 goes to x1 prime, x2 prime, which is this matrix, cosine theta, sine theta, minus sine theta, cosine theta, times x1, x2. Okay? All right? Now, here we go. Let's call the elements of this thing, cosine theta, sine theta, minus sine theta, cosine theta, by the following labels. Lambda 1 prime 1, lambda 1 prime 2, lambda 2 prime 1, and lambda 2 prime 2. Okay? So all I'm giving you is this way of notating the different elements of this transformation matrix in this sort of odd-looking notation, but you'll appreciate this notation in due time. Okay? First thing is to observe that the superscript is to the left of the subscript. And in general, when you're trying to take a matrix and represent it by a 2-index object, the row is labeled by the thing to the left, and the column is labeled by the thing to the right. Row 1 prime, row 2 prime, row 1, row 2.
Column 1.
Say it again?
Column 1. You said row.
Oh, sorry, column. Well, they're just horizontal rows or what? No, I mean, yeah, rows and columns, sorry. Yeah. Okay, here we go. I'm going to do this in gory detail. Here we go. So in index notation language, what we would say is that xi goes to xi prime, which is lambda I prime j xj. Okay? What I argue is that this expression contains all of this. Okay? And I don't need you to buy it, I'll show you explicitly. First and foremost, the language of matrix multiplication here, in this context, is going to be replaced by something called the Einstein summation convention. How many of you have heard of the Einstein summation convention? Sweet, about half the rooms and half the hands in the room came up. All right. Sean Mosier, are you here? Yeah, Sean. If I'm going to sum over an index on the right-hand side of this, which index do you think I'm going to sum over?
J.
J, yeah, you sum over repeated indices. Okay? So we want to sum over repeated indices.
Is that J attached to the lower J is attached to a lambda or the
Yes, this is attached to lambda. I won't be drawing anything with indices in front. I won't be drawing anything like this. Some people do that, not in this class. Yeah. Okay? So here we go. And I told you I'd do this in detail. So first and foremost, what we can say is the following. This is equal to the sum over j makes this lambda I prime 1, x1, plus lambda I prime 2, x2. I just did the summation over that repeated index. Okay? So this is x I prime. Now, to finalize it, what we do is we pick a value for I prime. So we've got two values in this story, so we can pick 1 prime, in which case this is lambda 1 prime 1 x1 plus lambda 1 prime 2 x2. Now, and this is going to be an easy task, so Kiana, Gus, what is this element of lambda?
I'm not sure. Sorry, could you?
What is the lambda 1 prime 1 element, or sorry, what is the 1 prime 1 element of the matrix lambda, or sorry, of lambda?
Isn't it cosine theta?
Yeah, it's this element, which is cosine. Good. So this is just cosine x1. What is the lambda 1 prime 2 element?
Sine.
Sine, exactly. Or sorry, these should be sine thetas.
Yeah, sorry.
That's what I did last week. I left out the damn angle. Okay? Now I just want you to take this and compare it to what you expect. If you matrix multiply this, what you're going to end up with is cosine theta x1 plus sine theta x2 and minus sine theta x1 plus cosine theta x2. Okay? So this notation just reproduced the upper line of this matrix equation. If I pick x2 prime and follow suit, I will reproduce the second line of this matrix equation. Okay, I won't write that down. Hopefully it's obvious that it'll be reproduced. Okay? Yes?
How do you distinguish between like squared and x with the upper script too?
Yeah, so that's a really that's a really interesting observation. Right now, well, actually, so in this class, there will occasionally be numbers that are squared, but most of the objects we will deal with will be variables versus numbers, and their components will be labeled by 0, 1, 2, 3, which I'll go over in a minute. But they'll also be labeled by mu, nu, lambda, so forth and so on. So in this case, it might be a little confusing. Is this x squared? Is this x to the 1? No, these are just labels of what we might call x and y. We're just calling them x1 and x2 because in the long run, we're going to sum over things, and summing over things requires numerical labels. Yeah, so you'll get used to this, I promise. Okay. All right, are there any questions about index notation before we move on? Yes?
So you guys have to define what your what the lambda's matrix is beforehand, like that. The cosine theta, sine theta is matrix equal to the lambda.
Yeah. So the lambda matrices can be very different things because the lambda matrices are just our transformations.
Yeah.
And they can, first of all, they'll be 4x4 matrices. Second, they could be rotations, they could be boosts, they could be a combination of rotations and boosts. So what you do is you write down the matrix, and then you say, okay, lambda this is this, lambda this is this.
Okay.
Yeah. Okay? Any other questions? All right, let's do it. So, there are several important things to note about this story. Starting with number 1. In 38 dimensions, who would want to write down the matrix version of this equation? Raise your hand. You just got volunteered, Lauren. Would you rather write down the matrix version of this equation or the index notation version of this equation?
Is neither an option?
No, you got to write down one.
Then I
No.
do index notation.
It's the index notation because the index notation of this equation is exactly the same. That's the equation. Doesn't matter how many dimensions you're using. Okay? Hence, size doesn't matter. All right? 2. This is important. We could have written xi goes to xi prime, and now I'm going to use a rotation matrix. Actually, let me just do it with lambdas. Let me see. Yeah, I think I can do it with lambdas. We could have written lambda, or xi goes to xi prime, which is equal to xj ri prime j. Okay? Now let's evaluate this. I sum over the repeated index. So this is going to be x, oh sorry, I meant to write lambda. Okay, so this is going to be x1 lambda I prime 1 plus x2 lambda I prime 2. Okay? If I pick out the values of the lambdas that I need, then I can evaluate that x1 prime is x1 times lambda 1 prime 1, which is cosine theta, plus x2 sine theta. That's the same damn thing I got down there. Everybody see that? What does this prove?
That's pretty easy.
Exactly. This is the commutation of this. You get the same result. Okay, so this is just an argument that you don't have to worry about the order in which things are written. Okay? Here's another important thing. You can immediately evaluate Mijk, Nijk, given the components of Mijk and Nijk. Okay? Are we scared?
Yeah.
Okay, you'll eventually learn how to work with things like this. But this is clearly something which goes way beyond matrix algebra. Something with 3 indices, can't do that with matrices. And all of these indices are contracted with all of these indices. How do you evaluate that with matrix? I mean, that's not just matrix multiplication, it's matrix multiplication plus a trace or something. I don't know. Anyway, we'll figure this out, okay? But clearly, if you can evaluate this simply with the index notation, then you can use index notation to describe things that matrices can't describe. Point 4. Upper and lower. These are not pills. These are, on these lambdas, there are upper indices and there are lower indices. Okay? Whenever you see a repeated index, they will always come in upper and lower pairs. Notice, I, J, K, J, J. Okay? In this class, you never want to repeat an index where both are upper or both are lower. You want one upper and one lower. That's a rule. We'll understand that rule in due time. Okay? I'm just trying to give you some working rules. Okay, so if you want to use the Einstein summation convention, you want to repeat an index, but one of those indices should be up and one of them should be down. Turns out it doesn't matter which one. Okay, but we'll discover why that is a little bit later. All right. In point 5, in 4D, we'll use, for labeling indices, mu, nu, lambda, etc., with values 0, 1, 2, and 3, which stand for CT, X, Y, and Z. Okay? Many people have a problem with this. They're like, if you're going to live in 4 dimensions, why don't you label your dimensions as 1, 2, 3, 4? Well, first of all, we can just as easily label them as 0, 1, 2, 3. Okay? But we prefer to put time at the beginning. So instead of labeling 1 as time, because this is really natural for X, Y, Z, we just label the T direction as the 0th direction. It's nothing big, okay? But that's going to be our standard. Six, primed and unprimed. Okay? You might get concerned that there's primes and unprimes all over the place. Okay, are you ready? Listen up. There is only one object in this entire class which will have a primed and an unprimed subscript or superscript, and that is lambda. Any other object in this class will have all of its subscripts and superscripts primed, or all of its subscripts and superscripts unprimed. Let me give you an explanation for why this is the case. Okay? Think about it. If I want to write down a vector in this unprimed coordinate system, then that vector has an unprimed superscript. If I want to write down the vector in the primed coordinate system, then the vector gets a primed superscript. The lambdas are what take me from the unprimed to the primed superscript. Okay? Because if you think about it, they take the unprimed superscript with the unprimed subscript of the lambda, you sum over these, and so you're left with this primed, and that's what explains this. So the lambdas have a foot in 2 different things. It can be a coordinate system and a rotated version of the coordinate system, or it can be a coordinate system and a boosted version of the coordinate system. but it's got a hand in one, which is maybe unprimed, and a hand in the other, which is primed. That's why the lambdas come primed and unprimed. Any other quantity in this damn class, we are going to consider in a single coordinate system. So if it's an unprimed coordinate system, every index should be unprimed. If it's a primed coordinate system, every index should be primed. Or, I can't remember what I just said. Did I say unprimed to begin with?
Yep.
And then primed? Okay, good. I was actually on it. Nice. Okay, does everyone kind of understand this? So I just don't want you to consider writing something like that. I want it either like that or like that. Okay? Don't worry, you'll learn what F mu is in due time. So the lambdas, and we're going to use the symbol lambda, okay, for all of them. The lambdas are the only time we have primed and unprimed subscripts and superscripts together. Last but not least, oh, man. Going back. It will often be the case that you might want to take an index notation equation and write it as a matrix equation. Because in the end, matrix algebra is a little bit easier to figure out than the index notation for like 4x4 matrices. Okay? You'll get practice doing both. But here is the very, very important thing. Remember, if you write an equation in index notation, order doesn't matter. But if you want to take that equation and cast it in terms of matrices, you have to get the right ordering. What's the right ordering? Well, it's very simple. Repeated indices must be adjacent. Notice, this would not give you the correct answer if you just put in the matrix. But the J and the J here are separated by the I prime. Here, where you know if you plug in the matrix for lambda and the matrix for x, it'll work out, the J and the J are immediately adjacent. Okay? So if you get an expression in index notation and you want to evaluate it using matrix algebra, which you're going to want to do, just rearrange your terms so that any repeated indices are immediately adjacent to each other. And we'll get plenty of practice doing that. Okay? Any questions? Okay, let's talk about vectors. Alright, so this is going to hopefully unearth some of your understanding of vectors into a more sophisticated understanding of vectors, which will eventually play into the definitions of dual vectors and tensors, spinning. No, we're not going to spinners, I'm just kidding. Gotta get this erasing done. Tell jokes while I'm erasing. You know, have any of you, no one in this room has ever been at Meyer Hall, have you? That was the previous physics building. I've taught this course in the lecture hall at Meyer Hall, where they had all of these chalkboards. They had these like 3 panels of chalkboards, but they all lifted and lowered. It was awesome. I never erased a damn thing. Yeah, anyway. So, vectors. Vectors. All right. So for vectors, first of all, we are dealing with space-time vectors. So everything that I'm going to say is specific to vectors in space-time, but I will just call these vectors. But I want to be a little bit careful because vectors can be applied to many, many different situations. You can describe the state of a system in quantum mechanics by a vector. Okay? If you're describing a state of a system by vector quantum mechanics, most of what I'm going to say does not apply to it. But in this class, whenever I'm working with a vector, it is a space-time vector, which means that it can be represented by a coordinate system and blah, 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 blah. Okay? So I'm just going to call them vectors, though. I'm not going to hang that word space-time on the front of everything. Vectors have magnitudes. Which may or may not be associated with things in space-time. Obviously, the displacement, the vector describing a displacement, the length of that has to do with space-time, whereas an electric field, the size of an electric field vector has nothing to do with space-time, right? Okay, so we have vectors which are associated with space-time in their size, but we also have vectors which are not associated with space-time in their size, okay? But the direction of any vector is associated with space-time. Okay? Obviously, your momentum can point this way, and the electric field can point this way. And those are the same directions in space-time. Okay? This is going to play a very critical role in our exploration of how do vectors transform. Okay, we're going to get to that in a moment, but let me say a few more things about vectors before we get going. So vectors have three important features. One, and this is probably going to bother you, and that's fine. Deal with it. Vectors are invariant under coordinate transformations. Now, that is probably going to bother many of you. Right? I mean, after all, like, what do we do? We can, oh, yeah, if I do this, and I'm going to X to Y, and then I do V, and I do X, X, and dash, and V's going to become D prime. Right? Yeah. No. No. A vector is me walking. That's my velocity. If I pick an x-axis along the direction I'm traveling, I'm going to have to just be an oscillator here. Maybe I'll walk more slowly. If I pick the x-axis along this, the y-axis, and the z-axis, and I describe the vector, I'll get one answer. If I pick the x-axis, I'm going to get the same vector. The vector is an existing thing. You can't change coordinates and change my vector. Coordinates are the way we describe things, but a vector is a physical thing, right? However, quite often in your classes, including your calculus classes, okay, you define a vector in terms of its components and the basis, but then when you talk about transformation, you only transform the components. You never transform the basis. Turns out, if you take a vector and you transform its components and the basis, you get the same vector back. We'll use that extensively, okay? Now, one of the reasons why this is so confusing is because if I have a vector and I'm like, oh, well, that direction and this direction are the same because my vector lives in R2, so I really can't tell that direction from this direction because it's just an infinite plane that looks the same in all directions. Okay, well, yes, fine. Put your damn vector on a cylinder. And now let me ask, is this velocity vector the same as this velocity vector? No. This velocity vector comes back and meets itself. This velocity vector does not. The problem is most of the context in which you've worked with vectors has been on flat space that's infinite, and direction doesn't matter. In this simple case, direction definitely matters. And in this class, when we curve space, direction will matter. Okay? So the idea that a vector is invariant under a coordinate transformation is going to play an integral role which you cannot get by without, like you could before. All right? Okay. We won't do much with topologically non-trivial spaces in this class, but that's just a really good example. Okay. 2. The components of a vector should have a well-defined transformation law. Okay? That is, if we transform the coordinates that we're describing our space-time with, the components of the vector should change. The vector itself does not change, but the vector itself are the components combined with the basis vectors. Okay? It's very important that we distinguish between those two. It's going to turn out eventually, I won't talk about it today, but eventually we will only work with the components of a vector. We won't worry about the basis. That's going to make our notation much cleaner. But I just want to point out, while the components of a vector are transforming, the vector itself is not. And then there's 3. And 3 is rather interesting. You have probably had one of the first vectors ever presented to you as the position vector. Right? Is this really a vector? No. You like to think of the position vector as the difference between the coordinates at one end and the coordinates at the other. So so the problem with the position vector is the position vector depends on the origin of the coordinate system. If I change where my coordinates origin is, I change the position vector. So the position vector is clearly not physical. However, if I have 2 objects, and I want to talk about their relative position vector, then that's physical. So is this a vector? No. It's not a vector. Can anyone guess why it's not a vector? Ben.
Hey,
Ben.
I'm not sure.
Good. Good. That's what I wanted to hear. I didn't want anyone to have an answer to this. So here's the deal. The rules of vector manipulation require linear algebra. Okay? Linear algebra is good on flat spaces. Okay? But the moment the space is curved, this shit doesn't work. If I have a curved space, and I want to talk about a straight arrow, well, let's draw a curved space. This is called S2, a two-dimensional sphere. I'm only talking about the surface of this. I'm not talking about the volume. So this is a two-dimensional surface. If I pick 2 points, and I say the vector from 1 to 2 is this arc, that's shit. Okay, that's shit because if I take that vector and I add this vector to it, I'm not going to get a vector which lives on the surface. And in fact, how the hell do I add these? It's weird, okay? So we have to abandon the notion that you can define vectors between points in a space. But then that sort of begs the question, where do vectors live? Because if vectors depend on flat space, and we're living on a curved space, what do? Well, this is the story. Vectors live in tangent space. That is, and I'm going to draw this on the S2, that is, if I pick a point, and I want to know where do the vectors at that point live, they live in a flat space which is tangent to that point of the circle. happens here. It's just it was never pointed out to you. If I have a vector, well, I'll take this one. And I don't even want to define a vector between points, because that's just bullshit. I'm going to pick a velocity vector. So the velocity vector seems to be extended from this point to this point. The velocity vector is defined at this point. This extension is just so that I don't draw a point, or give it a direction. Okay? But this vector is defined at this point, and this point lives in that part of the tangent space to this space. I mean, the tangent space is the same dimension as the space. Here, the tangent space is a two-dimensional plane because it's tangent to a two-dimensional surface. Here, okay, yeah, fine. There's your tangent space, it's three-dimensional, okay? Here's the important difference, though. If I want to talk about a vector over here, and maybe I want to add those or subtract those, then I can use the same damn tangent space. Okay? Because these tangent spaces have the same orientation. Do those two tangent spaces have the same orientation? No. No, they do not. So it turns out that working with vectors, if we want to compare vectors at two different points, if we want to take the derivative of a vector, which is built on the differential of the vector, the difference between the vector at a point and a very close point, we have to be able to move between tangent spaces which are not parallel. This will require some machinery, which we will develop. Okay? For now, we're just going to work in flat space, okay? But I just want to show you this because a lot of the machinery we're going to develop in flat space is going to allow us to apply it to curved spaces. Now, by the way, some of you might be like, oh man, where's curved space? Afraid of curved space. Actually, you should have been afraid of it here too, in flat space, because the fact that the tangent spaces are the same from point to point is critically reliant on the idea of using rectangular coordinates. If I decided to use polar coordinates, then the orientation of things changes as I move around. So the basis in the tangent space at each point is in different orientations. So it's actually only on flat space in rectangular coordinates that this story plays out really simply. You use curved coordinates, it won't play out. You're on a curved space, it sure as hell won't play out. Okay? Questions? Yes?
The plane on the opposite side of the sphere, is that in the same plane?
Yeah, so the plane on the opposite side would work, but we're not going to be interested in comparing this and this. We're going to be interested in continuously connecting, because we're ultimately interested in continuous functions, so things we can take the derivative of. So yeah, there could be 2 points where the planes have the same thing. I mean, actually, the planes could be parallel, but the coordinate system we choose on this plane versus this plane doesn't have to be parallel. The machinery we're going to develop is going to be able to work even if you change the coordinate choice as you move from one plane to another. So it's very powerful. That does happen now. Yes?
Instead of tangent space, why don't we use like three-dimensional polar to describe?
Three-dimensional polar?
Yeah.
Well, this is a two-dimensional surface.
Yeah.
So you can only use two coordinates to describe your position on it. And I mean, this is an instance where I could draw a two-dimensional surface, but you know it lives in well, this doesn't have to live in 3 dimensions. This is well defined, even if the third dimension doesn't exist. It's just, we live in 3 dimensions and we draw this for the third dimension. But let me ask you this, what about a 3-sphere? And I'm not talking about a ball with a surface, I'm talking about something which is the 3-dimensional analog of this surface. Can't even picture it. Yeah, no, it's wickedly challenging. So, but if you're dealing with a space which is, so you're thinking about embedding, and embedding is a very powerful tool for trying to understand a lot of geometry. But unfortunately, when we're doing general relativity, we're going to be talking about a four-dimensional geometry not embedded in anything. It's just the geometry of the space. Every axis is already part of this. It's not a curved space which is embedded in three-dimensional flat space in this case. That's just a special example. Okay. All right. So, as promised, we are now going to investigate. And I guess I said something here, but I didn't write it down. That's fine. Now we're going to investigate point number 2. What is the transformation of the components of a vector? All right. And I'm going to play this out very, very slow, but I am going to repeat this exact same story for more complicated objects. So please bear with me on the pace I take with this first simple familiar thing, because if you understand it to the point where you're bored, that's awesome, because I'm going to go a lot quicker as I apply it to more complicated objects. Okay, first of all, to figure out how the components of a vector transform under a space-time transformation, we need at least one vector where we know the answer. If we know the answer for a single vector, then we can figure it out for all other vectors. Can anyone guess what vector? Britt. Can you guess what vector we might consider where we actually know how everything transforms, and then we can take that lesson and apply it to a more general vector?
A vector, so, I mean, could it be one of the vectors that like we were just talking about where maybe if you're able to compare vectors crossing the same plane?
So I'm actually talking about, so before I gave you some vectors, I talked about displacement vectors, I talked about electric field vectors, momentum vectors. Is there any of those vectors which you think might be so intimately geometrical that we can understand the story for that vector?
I'm not sure. It would honestly just be a guess.
Okay, so anyone want to help her?
The unit vector?
Not the unit vector. So I'll give you, we'll just make this 1 out of 3. The displacement vector, the electric field vector, or the momentum vector? Which of those 3 do you think we could use? Any takers?
The electric?
Who says electric? Come on, kids, raise your hands. Oh, who says displacement? Who says momentum? Woohoo! Yeah! Turns out that they voted for momentum and displacement, and it's a couple of hands up for electric field. The answer is the displacement vector. Because remember, the displacement vector has a length in space-time, whereas the length of momentum is kilograms meters per second. That's not a distance in space-time. But a displacement, its length is a distance in space-time. So it's intimately connected to the space-time itself. Okay? So here we go. First of all, how do the coordinates transform? And the coordinates transform according to the index notation as x mu goes to x mu prime, which is lambda mu prime nu x nu. And those are nus and not v's. And those are mu's and not m's. Okay? Now, if this is the coordinate transformation, let me get a victim. PJ. I love it. Mask, no mask. How do you think a differential element of x mu? So we're not going to talk about finite transformations because I've already told you in curved space those are not going to be good. But we can obviously talk about differential. Because differential in the limit, two tangent spaces of 2 points should become parallel if the 2 points are coming together. So that's why we're going to do dx mu. How do you think dx mu transforms?
Would it be lambda d mu prime, mu x mu?
Sorry, well let's do this entire expression.
Okay.
So dx mu becomes,
Dx mu prime.
yes,
Okay. Lambda d mu? I don't know why, but like you're kind of changing, yeah. Prime. It's like you're changing the basis as it goes through, but I don't.
so this is a vector in one coordinate system, this is a vector in the other coordinate system, and this is the transformation that takes me from this to this. This is a vector in one coordinate system, this is a vector in another coordinate system.
Okay.
What transformation do you think I need to carry me from dx mu to dx mu prime, like I did here?
Still just the lambda.
It's just the same lambda, yeah.
Uh,
The lambda part of the story is exactly the same.
Okay.
Okay, everybody on board with that? We're just replacing the x mu's with dx mu's. Okay? Well, we know how the components of this vector transform. However, so this is actually a vector. This is not a vector, these are the coordinates. So let me stress this. This is a coordinate transformation. These are the components of an infinitesimal displacement vector. Are we on board? It just turns out that these transform exactly like the coordinates. Because these are just differentials. They're just a coordinate value minus another coordinate value. So they transform just like the coordinate values themselves. Okay? Now here comes the story, which we're going to play out again and again and again. Here we go. Recall, a vector is invariant under a coordinate transformation. So what that means is the following. First of all, these are the components of a vector. We need to give the vector a name, and we're going to call that vector ds. I don't want to call it dx, because dx is a little confusing. It's like x, is that just x? Is it xyz? Is it x1, 2, 3? So we're just going to call this ds. That's our standard notation for displacement. Okay? And then what we can write is that ds has the components dx mu but ds is the whole vector, so it is the components combined with the basis. And the basis I'm going to label in this weird way like that. Okay? Now, here's a very important thing. This is labeling the component of the vector. So if I just wrote down the vector's components, I might have A, B, C, D. So this might be dx0, dx1, dx2, dx3. This is not labeling the components of the basis. Each value of mu here is a separate basis vector. Okay? So let me just give you a picture to associate with this. And again, I'll just work with two-dimensional pictures because drawing four-dimensional pictures is just not my thing. If we're living in 2 dimensions, we can label its coordinates by x1 and x2. And then we can adapt a coordinate basis, which is given by these two vectors, e hat sub 1, e hat sub 2, and of course the hat means normalized. Okay? Now, this thing is invariant. This is an entire vector. So this should be invariant. We know how this transforms, so that should be enough to tell us how this transforms. Okay? Everybody on board? And again, I'm going to play this out a couple of times, but I want you to really understand it in this first round. Because in further trips, it's going to get more complicated. So here we go. Dx mu e hat mu goes to ds prime, which is composed of the transformed components of the vector combined with the transformed basis vectors. And if ds is invariant, this should be the same as the ds we started with. Okay? So now I know how dx mu transforms. I just use this. So I can write down lambda mu prime. And let me just figure out what the hell indices are. Okay, so I'm going to say mu dx mu e hat mu prime. Okay? All I've done is I've replaced the components of the transform vector with lambda mu prime mu dx mu. Okay, that's the expression for the components. I haven't done anything to this yet. Okay? Now we're going to write down something for this. We don't know the answer. We can just guess and then figure out what our guess means. So I'm going to guess, first of all, we write down what we already know. I'm going to guess that there's going to be some lambda, and it's going to give me this lower mu prime. It's going to have an upper index, which is unprimed, and it is summed with the index that this basis vector carries. So if you just look at this for a moment, alpha is summed over, so it will disappear, and this will be left with a lower mu prime, which is what we have here. So this should at least make sense. Yes? Good. Das ist gut. All right. So here we go. First of all, order doesn't matter. I can rewrite these in any order that I want, and so I can write this as lambda alpha mu prime lambda mu prime mu dx mu e hat alpha. I just rearranged them, that's all I did. Okay? If lambda alpha mu prime lambda mu prime nu equals, okay, hold on, look. What do we want this entire thing to be equal to? What do you think? What do we want this entire expression to be equal to?
It's going to have to equal dx mu e mu, the original ds.
Yes, this has got to be the same as the original ds, which is given by this. So this can be given by e dx mu e hat mu. Ross! Sorry.
Yeah, hi.
What does this have to be equal to?
Delta alpha nu.
Yes. Delta alpha nu. Where delta is the Kronecker delta function. That is, it's 1 if the values of alpha and nu are the same, and it's 0 if they're different. So a delta alpha nu just forces the mu and alpha to take the same values, which is what this means. Okay? Take a moment and digest that. Yes?
I think this is like a really silly question.
No, there's no silly questions.
There might be.
Yeah, go ahead.
So, okay. So in that big string of things that you just read at the bottom,
Yes.
in the, I guess like the first term, because the second term is kind of an extension on that, but we can talk about the first term. Yeah.
This one?
Yeah. So, why is there no mu or like mu in it? Like, why are we using mu instead of mu?
Because, well, we could have used new.
Okay.
We could have used new. But what I knew I wanted to do, look, okay, so to be fair, Lauren, are these two any different?
I suppose not.
No, they're not.
It's just-
So I could have just called this new, and in that case, this would have ended up being dx nu e nu, but some of you might have been like, well, that's not what you started with. You started with mu's. That's the reason I wrote mu instead of new.
Okay.
Is that,
Yeah.
yes?
Yeah, just to kind of build off that, I might have missed something that you said when I was taking notes.
Okay.
Why exactly does mu come in on the term where it's like if lambda alpha mu a lambda?
Oh,
mu
shoot,
prime?
hold on. No, sorry, you're right.
That statement's still true. It's just, you just replace mu.
Oh, sorry, no, this is not what I want. I want this.
Okay, thank you.
Sorry, my bad.
No, you're okay.
Yeah, my bad. I think I have it written correctly in the, yeah, it's written correctly in the notes, I just copied it down right. No, I actually have it written down wrong in my notes. Sweet, I copied down, yeah. So yeah, this is supposed to be a mu.
That
Okay.
makes more sense.
Now, if you look at this expression, something times something else equals,
Something else.
what is this? I mean, what is it effectively? If you think of it as a matrix. If you think of this as a matrix, this labels the rows, this labels the columns. It's 1 if the quantities are the same, and it's 0 if your quantities are different. It's the identity matrix.
No way.
Okay? Well, this is something times something equals the identity. How is this related to this?
They're inverses.
They're inverses. So if we call this thing lambda, then this is lambda inverse. Or maybe this is lambda and then this is lambda inverse. It doesn't matter. Okay? Now you might be tempted to say, oh wait, I know what lambda inverse is. Lambda inverse is just lambda transpose. That's wrong. Okay? That's true if you're doing rotations, because in rotations in normal 3-dimensional or 2-dimensional space, rotations satisfy this orthogonal identity. So the transpose of a matrix is the inverse of the matrix. But in general, the transpose is related with the metric G, so not the identity. Okay? All right. Now we're in a position to finish the story of how a vector transforms. Here's the story. ds equals dx mu e hat mu goes to ds, or I'm just going to write down the expression, dx mu prime e hat mu prime, which is our expression for ds prime, which should be the same as ds, if dx mu transforms according to this rule. I'm just summarizing what I've gotten so far. And E hat mu transforms to E hat mu prime, which is equal to lambda alpha mu prime E hat alpha. Okay? And lambda alpha mu prime nu is delta alpha nu. So I'm telling this story now with nu. Okay, so I'm not following the rigors of this, but this is a complete and accurate story. Okay, so I'm going to put this in a box. All right? This is the transformation in its entirety for one vector. That is the displacement vector. We're good? Well, we've got a few more vectors to go. No, I'm just kidding. So, we can take this story and immediately find the transformation for an arbitrary vector. Okay? Think about it for a moment. ds is a very special vector. Its components are dx mu, e hat mu. What would an arbitrary vector look like? What do you think? Any takers?
It would have other components besides dx mu on the basis vectors.
Yeah, it would just have a set of components associated with where this is extended to. So if this is meters per second, these are meters per second. But these are just the basis vectors. These are the coordinate basis vectors. They're what you're going to expand any vector in. These capture the direction that's common to all vectors. The components capture the magnitude, what direction it's extended. You ready? I'm going to cheat. Here we go. Boom. A vector is invariant if the components of the vector transform in this way and the basis transforms in this way, where the transformation matrices satisfy this. So again, we started with the displacement vector, whose components we knew how they transformed, because the components of the basis vector are just their differentials of the coordinates, and we know how the coordinates transform. So figuring out how the components of this vector, ds, which are just dx mu's, we knew how those transformed. Then we used the transformation of this to figure out the transformation of this, but knowing the transformation of this, which is common to any vector, allows us to figure out how the components of any vector transform, and they transform in exactly the same way as the coordinate differentials. Okay? We're going to use that story in several more contexts. Are there any questions about it? Okay, so I just want to go through one concrete example very quickly of showing you how all this plays out using the summation convention, doing matrix multiplication and everything. And then we'll give it a break. And on Thursday, after your quiz, we're going to take up the idea of dual vectors. So I'm just going to erase everything and we're going to bust out. And I'm going to do this rather quickly. We're going to bust out a concrete example. So here we go. First, I'm going to do a two-dimensional example, obviously, because I can't draw 3 or 4-dimensional things. I'm going to use the basis vectors I hat, j hat, and I'm going to talk about this vector v. Okay? So we know the vector v is vi hat plus 0j hat, because vector v points in the x direction, that's the direction of I hat. In index notation, we would call this vi e hat I. Okay, now just very quickly, when we're dealing with space-time, okay, we use letters like that. When we're dealing with just space, either one or two-dimensional space or three-dimensional space, then we use labels like this. Okay, so that's why I'm using I instead of mu or nu. Okay, so we're just dealing with spatial directions, where e hat 1 we can take to be I hat, which is 1, 0, and e hat 2 is j hat, which is 0, 1. Okay, so there's the matrix realization of these things. All right, so according to this, v1 equals v and v2 equals 0. This is the v1 component, this is the v2 component, so this is v, this is 0. I'm just identifying the components. And now, what we want to do is we want to just change our coordinate system by rotation by 90. All right? To do this, we rotate by 90, which we know what that looks like. Cosine 90, sine 90, minus sine 90, cosine 90. Oh, that's an easy one. This is just going to be 0, 1, minus 1, 0. Okay? And we are going to take this to identify the elements of the rotation transformation. I'm going to use R here because we're really talking about a rotation. I would use lambda if we were talking about space-time, but this is rotation, so I'm just going to use R. Okay? Now, to describe V in the new coordinate system, what we do is we say, okay, we know VI goes to VI prime, which is RI prime J VJ. And this tells us that V1 goes to V1 prime, which is R1 prime 1 V1 plus R1 prime 2 V2. Okay, I'm just using the summation convention on J, so I'm doing 1, 1 plus 2, 2. Okay, and now I'm going to take I equals to 1, and then of course V2 goes to V2 prime, which is R2 prime 1 V1 plus R2 prime 2 V2. Okay, but now we can figure out what these are, because we know the elements of Ri prime J. What is R1 prime 1? 0. What is R1 prime 2? 1. R2 prime 1? R2 prime 2? R3 prime 3? I know. Pretty funny. Okay, so this is going to be 0 and this is going to be minus V. That's what it works out to be. Okay? This is just plugging in this information and this information into those expressions. Now, I want to rotate the vector, so I also have to tell you how the basis vectors transform. And the basis vectors in this case are going to transform by the inverse of the 90-degree transformation. But what's the inverse of a 90-degree rotation?
90-degree rotation.
Transverse.
Yeah, it's a negative 90-degree rotation. Okay? And this we can almost immediately write down as 0, minus 1, 1, 0. Okay? So this is going to constitute the elements of R, J, I prime. Okay? Which is what we need in order to transform the bases. So here we go. We have E hat I goes to E hat I prime, which is R, J, I prime, E hat J, which is, okay, which is R1 I primed E hat 1 plus R2 I primed E hat 2. I'm just summing over the repeated index, and the I still hangs out in the expression. Okay? Now we can pick different values of I. So we can say E hat 1 prime comes out to be R1 1 prime E hat 1 plus, and I'm almost at the end of the story, so if you bear with me, I know we're a couple of minutes late, but this is going to be complete. So to figure out the 1 prime component of the basis vector, we just take R1 1 prime E1, R2 1 prime 2. I'm just labeling the I here the same as the I's here. Okay? R1 1 prime. What is R1 1 prime? 0. R2 1 prime. R2 1 prime is 1. The leftmost index is telling me the row. Okay? So if I take these, 0 times E1, 1 times E2, then this is going to end up being 0, 1. Okay? And then it's written in my notes, but I won't bother writing it explicitly here. If I also transform the second basis vector, I get minus 1, 0. Okay? Comparing, notice I hat prime, okay, that's E1 prime, is related to I and J in what way? It's J. What about J hat prime? Negative I hat. Is that what we expect?
Yeah.
Yes, it is. And last but not least, the vector, which was vi hat plus 0 j hat to begin with, becomes 0 I hat prime minus v j hat prime. Those are the same vectors. Can everybody see that? Can you see it? See it now? Good, we're done. Again, feel free to look at the notes. Joel, did you stop it? Joel, did you stop it?
Huh?
Did you stop it?